right. 12:38. So we start at 12:30. Progress has been made in research and engineering, focusing on the mechanics of flying, swimming, and locomotion over land. Oops, it shouldn't be on this side. Extraction, blah, blah, blah. Restarts extraction. Then update. All right. Progress has been made. All right, so how am I going to start this? I'm going to say here. So they've done a lot of research and engineering, focusing on the mechanics of flying, swimming, and locomotion over land. That's out there. They have done a lot of research. Done a lot of research and engineering, focusing on the mechanics of flying, swimming, and locomotion over land. This has led to many useful applications and has furthered our understanding of the mechanics of such types of locomotion. However, locomotion through granular media is still not well understood, and neither are the mechanics of tunnel formation. And really, in terms of application, a few burrowing machines exist for practical application that match the performance of living organisms. A better understanding and application of the principles of excavation and movement within granular media can be relevant to a variety of fields, including construction, resource extraction, interplanetary exploration, and search and rescue. Soil mechanics, organisms. Okay, I see. I see. All right, let's try this again. 1241. Progress. So, thesis proposal. Yeah, here we go. So, they've made a lot of progress in research and engineering, focusing on the mechanics of flying, swimming, and locomotion over land, which has led to a lot of useful applications and furthered our understanding of mechanics of these types of locomotion. But the locomotion through granular media is still somewhat poorly understood in comparison to these other things. The mechanics of tunnel formation is not quite understood. And when it comes to applications, there's few machines that exist that match the performance of living organisms. And so, all in all, a better understanding and application of the principles of excavation and movement within granular media can be relevant to a wide variety of fields, things like resource extraction, construction, interplanetary exploration, and search and rescue. The difference, oops, is important. Left out something there. Search and rescue. So where is the slide? Research. Let's see. There again. And okay. Research is generally more often focused on dry granular media than on damp granular media. And that's an important difference because the mechanics can be quite different depending on whether it's damp or it's dry, just depending on the moisture content of the media. For example, dry sand can be made to flow, sort of liquid like when a force is applied, which allows some organisms to adopt strategies analogous to those for moving through a low Reynolds number fluid. As you add water, capillary effects and surface tension uh, begin to increase the cohesion between the grains so that you have a damp granular media showing more plasticity, an increase in shear strength, and history dependence as a result of this increase in moisture content. However, if you add enough water, it's going to become saturated. It enters this slurry state, and capillary action no longer holds the grains together. So you kind of lose this cohesiveness. But in general, penetration resistance decreases with an increase in moisture content in cohesive soils. Now, with these differences, it means that locomotors moving through damp granular media are unable to use some of the strategies they would be able to use in dry granular media. Uh, but the cohesiveness of the substrate means the grains are formed from tunnels or burrows that can then stay in place once created. In terms of the logistics of research, some of the lack of research involving damp granular media might be partly due simply to these challenges when it comes to experimental setup, especially in regards to things like numerical approximations, also preparation of repeatable trials. When you're looking at locomotion through dry granular media, you can at least approximate it through things like resistive force theory, in which you're looking at locomoting an object through sand. It's being theoretically divided into infinitesimal segments, and the thrust and drag experienced by each segment can be summed to approximate the forces activating on the locomotor as a whole. And that's kind of what's being illustrated in this picture here. It's showing this infinitesimal segment and just the forces that are going to act on that. Anyway, this can work in dry granular media because movement through dry grains, like the cohesion of damp granular media, is not history dependent. So, in other words, the forces experienced are not changed by past movement through a given location. It can move its head, it can undulate through the sand, and it's not going to affect the forces that are acting on the rest of the body as it moves. So an undulating body or rotating head can thus be approximated through the integration of forces across all segments if movement is taking place at a sufficient depth below the surface. So, as mentioned before, the addition of water to granular media leads to cohesion between particles, and this creates this history dependence that influences the forces encountered by segments during locomotion through the media. Uh, so, trailing segments will encounter the surrounding media in a different way depending on the movement of the leading segment. Now, from a purely logistical standpoint, it's more difficult to prepare repeatable laboratory trials for testing damp granular media than dry. You can use fluidized air beds. If you're looking at dry granular media, that's a lot of help. You do your test, you run air through it, and it resets the mechanics back as though nothing had happened. You can't do that for damp granular media. It's unable to be fluidized like that. There have been some methods developed to deposit homogeneous batches of damp granular media, but they still require the testing area to be emptied and refilled each time, which can be labor intensive and time consuming. But in terms of research, I mean, worth it. Despite the challenges, damp granular media is a common substrate, and it's actually more commonly encountered in terrestrial habitats than dry granular media. So somebody's got to look at it. Um, And a lot of research that's been done involving dry granular media, it can't really be assumed simply to relate to locomotion through damp granular media because of the different mechanics. Change this. So as a result, locomotion through damp granular media is an open and an attractive area for academic research. Organisms that move through granular media have quite a diverse range of kinematic strategies, even among those of similar body plans. This is especially evident in Amphisbaenia, which is something that we'll be looking at here. This is amongst Amphisbaenia, which will be of particular focus in this thesis. Duplicate slides, get rid of this one. It will be of particular focus in this thesis. These animals tend to be underrepresented in literature. This is partly because they're elusive, they're hard to find, they're underground, but they're also difficult to keep alive in captivity. They're very successful in moving through compact soils. They can invade niches that are inaccessible to other reptiles. This, of course, makes them very attractive for bio-inspired engineering. And finally, distinctive head geometries and the relative simplicity of movement are very advantageous in making robophysical models. Some of the biology, some of the background in Amphisbaenians, they seem to prefer moist substrates. Moist substrates. Carl Gann suggested this is related to the water permeability of their skin, but he also hypothesized that this was related, at least in part, to the ability to form a substrate into tunnels. Now, of course, once you've created your tunnel, the energy requirements for moving underground is really decreased. Also, the energy required for breathing, for just respiration, um, is decreased because otherwise the animal's pushing against this burden of material as it tries to breathe. When it comes to locomotion, Amphisbaenians appear to have developed several adaptations to aid in their subterranean locomotion, which includes limblessness, elongation, robust skull. These are adaptations often associated with fossoriality in other organisms. Uh, but Amphisbaenians have also developed distinct kinematic strategies to aid in locomotion and tunnel formation. One of the interesting things about that is that these strategies appear to be correlated to specific skull shapes, which results in four rather distinct patterns that couple morphology and kinematics. There's three specialized ones and then the more generalist one. The most widely distributed pattern is just this generalized rounded or bullet-shaped skull. It moves apparently using random movements through the media that it's moving through. And this can be either with the forward penetration or decoupled from the forward penetration intermittently between the pushes. When you start to get into this specialized thing, there's one that involves sort of a corkscrew type motion. It combines a rotational twist with a simultaneous forward penetration movement. Corkscrew, pretty much. This is correlated with the sharp edges on either side of the snout, which then act to shave off the material from the surrounding media as the animal moves. This appears to be advantageous in sand and more sandy soils. It allows for rapid burial in hot and dry environments to access cooler and moister substrates. This is pretty much exclusively found amongst members of the Trogonophidae family of Amphisbaenians. Interestingly enough, these are found in sandy soils in North Africa and the Arabian Peninsula. So another pattern involves a side-to-side rotation of the head that is simultaneous with forward penetration movement. It is. Okay. You can actually have a look at that. Now, in this case, the skull is flattened laterally, so the head resembles a wedge shape, so it's keel snouted. Make a note here. It's also known as a keel snouted Amphisbaenian. Another pattern of morphology and kinematics is the shovel snouted type, so it has this kind of dorsally flattened shovel-like head that it rams into the substrate, lifts to pack into the ceiling, while simultaneously pushing its ventral side into the floor, flattening that down. So the keel and the shovel-snouted types are found in more compact and deeper soils than trogonophids or amphisbaenians with the more generalized morphologies and kinematics. Overall, these things seem to be geographically. These things seem to be, what's the word? Distributed geographically. Trogonophids, keelsnouted amphisbaenians are separately distributed. What's the word I'm thinking of? Are separated. Separated. The range of the generalized types can overlap are allopatric, I think is the word, right? Allopatric. The range of the generalized types can overlap with any of the three others. In terms of the decoupling the head oscillation and the forward penetration, Carl Gans thinks that this results in increased mechanical efficiency when it comes to burrowing. The intermittency of the motion should theoretically increase the force applied to the substrate simply because force is directly proportional to acceleration. So if you have multiple short bursts of acceleration, you're going to have more force applied than one continuous push. This is kind of how pile drivers work. I have a picture of a pile driver there, but Gans likened it to that. You have this ramming, short ramming motion rather than continuous push. These suggestions in terms of the decoupling and the intermittency are hypothetical. Of course, there's a lack of published data comparing strategies. Sharp, Sarah Sharp in the Goldman lab in 2014, 2015 did an experimental study involving observation of the burrowing behavior of the oscillated skink. These employ a side-to-side head rotation that is simultaneous with forward penetration. A hypothesis for why they do this kind of thing is that it weakens the resistance of the media, thereby decreases the force needed to penetrate. They kind of liken it to the crack propagation almost of breaking up the substrate in front of the animal, sort of like earthworms do when they expand their front segments. There's a couple other hypotheses as well. That's kind of the one that I'm going to zero in on. And they looked further at this. It prompted a mechanical simulation that looked at drag forces following the rotation of a cylindrical rod. So they found that if they did a side-to-side rotation of this rod and then had it push forward through the media, it lowered the drag force of this intruder, which was a little transient. It disappeared after about 4 centimeters. And that's about as far as published experiments have gone with this sort of thing. It's really lacking when it comes to a relationship between a repeated head rotation during penetration and the overall forces required. So I did my preliminary research has looked at this. And found there is this transient advantage that Sharp et al. Found there. So that's represented by that dashed line is following the rotation. The solid line is without rotation. And so here I have with no rotation is the blue lines. The green and the brown lines are following rotation at two different amplitudes of head motion. And it shows that both of them really at 2x here means two head rotations per push per per extension of the penetrator. But anyway, you can see this is decreased and it stays pretty steady as it goes there, especially if you look at those brown lines. Looking more specifically at the parameters, it seems the energy advantage depends on the number of head rotations relative to forward penetration. So that's where I have 2x, meaning two head rotations with one forward penetration. Less so on the amplitude of rotation, at least beyond a certain point of amplitude. And by amplitude, I mean how wide the head is sweeping. So, presumably, as rotating the head more often and at a higher amplitude incurs a greater cost of energy, it's kind of implied there might be optima for these variables outside of which efficiency is lost. Um, and descriptions of the preliminary results I'll cover in more detail in the relevant proposal chapters. The forces involved with burrowing are a lot higher than many other forms of locomotion, and the energy it costs associated with this means of locomotion is, you know, also a lot higher than any other. This being the case, it would make sense that burrowing should lead to selective pressures that drive the morphological evolution of burrowing organisms. And in fact, burrowing organisms tend to share some common traits. Convergent evolution, it appears to favor a narrow, elongated body shape, a reduction of the limbs, and a decrease in size. At least superficially, this seems to take place across many different animal types, from birds to mammals to reptiles to invertebrates, um, and so on, sort of suggesting how strong a selective pressure burrowing uh, seems to be. And theoretically, these resistive forces might drive head shape as well. Geometry plays a big role in the forces required for penetration. Experimentation has shown that narrow and generally more conical shapes experience less resistance to penetration than other shapes with wider diameters. The thing is, this can be complicated by other selective pressures, such as feeding. This is a big thing when it comes to skulls shape as well. These can constrain the head shape of burrowing organisms. And also, kind of hinted at, as we kind of talked about here, organisms with different head shapes can adopt different strategies of head movement during locomotion, which will then change the effect that any specific head shape is going to have on the forces experienced by the locomotor. So this would in turn lead to differences in optimal head geometry for a burrower based on behavior. Um, a study done by Lowy et al. In 2021 looked at head shapes in relationship um, to the push forces of caecilians while burrowing. They found there was no significant relationship. In this case, they didn't think the head shapes differences were a result of selective pressures of fossoriality alone. The head shapes, though, of caecilians are not nearly as drastic as those that are seen in specialized amphisbaenians. They also didn't look at movement strategies. So the question is really still open, despite some of the research that's been done in this area. So the thesis intends to address the knowledge gaps in our understanding of how head-shaped and kinematic strategies impact the forces involved for burrowing squamates, particularly in damp granular media. And so specifically, the topics I'm going to look at include the effect of varied rotation ratio and amplitude on the forces required for burrowing, the effect of intermittency as opposed to simultaneous push and rotation. Um, so whether the animal's rotating the head while pushing forward or stopping its forward push to rotate the head before continuing the forward movement. And finally, an analysis of head geometries in combination with kinematic strategies. The research is going to involve a robophysical model, which is a mechanical device that simulates the geometry and kinematics of the organism of interest. Robophysical models have advantages over using live organisms due to the elusive nature of animals, such as amphibians, the scarcity of finding them alive in captivity. But robophysical models also have advantages in the fact that they're programmable, which is of enormous benefit when studying locomotion underground in an environment that cannot be observed visually. We can control the movements of the test subject and be sure that it is performing these movements even when it cannot be seen. You can also eliminate variables so that the experiments can focus only on factors of interest. The robophysical testing apparatus being used for this thesis consists of a 3D printed cylindrical shaft and a movable head, actuated by hydraulic pistons. The model reconstructs the head motion and forward penetration of a burrowing squamate similar to an amphisbaenian. There's a piston that extends and retracts the shaft. A second rotates the head through a slider crank mechanism. These are connected through hydraulic tubing to two driving pistons, each coupled to a stepper motor driven worm gear by a 3D printed load cell. Deformations in the load cells are sensed by two 350 ohm strain gauges connected to a half Wheatstone bridge configuration to a custom amplifier designed by Kalen Gamble in our lab. Voltage output is recorded using a NIDAC system and MATLAB to record the changes in load cell deformation caused by the force acting upon the driving pistons. Calibration allows for these voltage outputs to be converted to force in newtons. The hydraulic system, as opposed to pneumatic system, is essential. In this case, the position of the submerged penetrator can be known even though it's not visible. Hydraulic fluid is incompressible, whereas something like pneumatics is compressible. But since it's incompressible, it allows for a direct one-to-one transfer of motion from the piston to the robot, so that you know whatever distance the driving piston is going is theoretically the distance that the shaft submerged under the sand is going. The stepper motors are controlled through an Arduino system. One of the limitations with Arduino is that it tends to only want to do one thing at a time, so it'll only run one stepper motor at a time. I want a head and a shaft moving simultaneously, so I'm basically using two Arduinos here. Um, One board contains the code for the shaft, and the other one contains the code for the head. Um, the head, the head Arduino is sending a signal to the shaft Arduino so that when the head starts, the shaft starts. This way, they're synchronized. They can both be operated simultaneously. There's a potentiometer in the head of the robot in this newest system. I don't think I put that in the um, thesis proposal. Before I was just counting the steps myself, trying to figure, calculating hard, writing it into the code, um, how many steps the stepper motors need to take. This way, it automatically does that. I put a potentiometer in there so that the robot knows what position the head is at, so the desired angle of excursion can be programmed rather than having to put in all the steps. And then this angle is verified just using a protractor before beginning a set of trials. And I wonder if this is necessary here. One time, because the system's operating slowly. Let's move this slide to the end in case anybody asks me about it. Oh, where was I? Morphology. The head is easily detachable, press fit on a shaft, extending from the potentiometer. In this way, the variable of the head shape can easily be changed to swap out one for the other. Head pieces of different geometries will be designed and printed, inspired both by existing morphologies and geometric shapes. Head pieces of different geometries will be designed and printed. That. Huh? Following a simplified version of the method used by Sharp et al. In 2015, we built a system for homogeneous deposition of damped granular media, which simply involves a hand-powered shaker screen with quarter-inch mesh. This is suspended above the testing area. Damp sand um, has been shoveled into the screen. The updated version now uses a winch system so that um, instead of having to shovel it in, I can just lift the one tub so it is above the other tub, and then hand shovel it down through a hole in the side of the tub. Um, but this is the way we've been doing it, is just by shoveling by hand and then shaking through. This kind of soil raining deposition was found by the Goldman lab to produce a more even and homogeneous distribution of sand. Otherwise, there'd be voids that form the sand if you were just to shovel it straight in. And this could interfere with repeatable results. And this method is kind of validated simply through repeated trials where robotic penetrator, the mechanical properties, when deposited this way, seem to indeed be comparable among replicate trials. So sand is shaken into a large tub until the container is filled halfway, at which point the robot is attached to a fixture mounted to the side wall. Sand is then deposited to fill the remaining volume, leaving the robot submerged at the midpoint of the container and thus minimizing edge effects. Since the model is connected to the driving pistons through hydraulic tubing, the robotic penetrator can be anchored to one side of the testing area and driven horizontally into the sand. This eliminates depth effects. Otherwise, vertical penetration into granular media is subject to a pressure that increases proportionally with depth. The force required to operate the system without submersion in sand is first recorded to be used as a baseline. That's the red lines here. Baseline is then subtracted from the recorded forces during data analysis. Um, the recorded forces are the green line here. The subtracted, and therefore the forces of just the pushing without the whole force required to operate the system can be seen there as the blue line. Uh, a fast Fourier transform is done, followed by low pass filtering to smooth data, and then forces can be calculated after the filtering. So the forces required for penetration in this case involve two main components, and therefore we're looking at two different things. One is the force involved with pushing the penetrator forward in the substrate. The second is the force involved with moving the head, should head movement strategy be employed. The forces involved with the head movements will need to be considered in order to observe the potential trade-off between a reduction in penetration force and an increase in rotational force. Each session involves the same basic steps. Parameters are set. Routine maintenance needs to be done. You make sure everything's working properly. Make sure there's no air leaks in the lines. Make sure the wheatstone bridges are zeroed. These sorts of things. The test run is done. Um, Not every time though. Mhm. Working properly, tiny air bubbles can be trapped in hydraulic lines, often involves bleeding of the air. I'm not sure they need to know this either. Well, maybe we want to test that. Tiny air bubbles. So this part, I don't think this. Let's see. The robot is given a test run to ensure proper functioning. A small protractor temporarily mounted to the penetrator just above the head allows for visual confirmation that the desired angle of excursion is being reached during the head sweep. Distance of the shaft extension can be confirmed using a meter stick. The Wheatstone bridge circuits are zeroed. A multimeter is used to ensure the bridge is balanced. For the trials, minor adjustments of resistance being made using built-in potentiometer in the circuit. While the circuits are zeroed, the load cell couplings are detached from the driving pistons and the lead screws are detached from the motors so that the load cell coupling units freely slide on the guide bars. This ensures there is no external force acting on the load cells whilst zeroing. What if we really need all this? Probably not. Let's take this out too. Put this in an extra slide. Sand is deposited through the shaker screen until the test arena is filled halfway. At this point, the robot is attached to the mounting in the arena, and sand is deposited to reach the final depth. This puts the robot at an equal distance of 15 centimeters from the top and bottom, and equal distance of 16 centimeters from each side. The head of the robot is at a starting position 34 centimeters from the end wall of the test arena, which is 33 centimeters from the back wall. And it ends up at a position of 24 centimeters from the end wall of the test arena, which is 43 centimeters from the back wall. MATLAB starts recording the data input gathered by the NIDAC. The machine is engaged in the predetermined testing parameters. Following each trial, sand is sampled to monitor for potential changes in moisture content over time, such as those due to evaporation. I don't know if I need to go into all that, do I? My first parameter robot test run Wheatstone 0. Okay. Then the penetrator is excavated from the sand-filled test arena. Load cell calibration is done by vertically orienting the load cells and attaching them to a metal frame that allows for weights to be suspended from them by Kevlar thread. In the case of the shaft load cell, uh, the screw is set in the top, the thread is looped around this, the weights can then just compress the cell. The head load cell calibration is a little bit more difficult because it's in both compression and tension while the machine is running, so we have to pretty much turn it upside down to get the tension forces and hang the weights as opposed to compress the weights. Folded readings are taken as an average of 3,000 data points for each weight. It's multiplied by 9.81 meters per second squared, the acceleration of gravity, which then gives us the newtons, the force in newtons, equivalent to the weights. Okay. This is plotted against the folded measurements. Give constant conversion factor so that all of the readings taken during the trials can be converted into voltage, from voltage into force. So this brings us to the first actual project. After we've gone through all this background, the effect of varied rotation, ratio, and amplitude on the forces required for burrowing. So an amphisbaenian side to side and vertical head movements probably function to compact soil into the sides or the roof of a tunnel. Although in the case of oscillated skinks, they do the same motion in both dry and non-cohesive sand. So in non-cohesive sand, they're not making tunnels, which then kind of opens the question, is that always the reason that these organisms, is that solely the reason amphisbaenians are doing it, I guess. Is that the way to put it? Yeah. Anyway, the reason oscillated skinks do this is unclear. One hypothesis is that the movement, um, since it's done in dry sand as well as damp sand, is not just necessarily making tunnels, but also decreasing the required penetration force. There's a lack of published data quantifying the parameters of head movement, such as amplitude, which I define as the excursion angle from the center point, and the rotation ratio, which I define as the number of head oscillations per unit distance, and the influence that variations of these parameters have on the performance of an organism. So there are still open questions. To address these issues, these parameters of movement of the head of the above-mentioned roller physical model are systematically varied. We'll look at the performance in terms of the force and work required to penetrate and move through wet granular media, taking into account the forces and work required to both penetrate and rotate the head. Head rotations of 0, 1, and 2 oscillations per shaft extension have been tested at excursion angles of 0, 15, 17.4, and 27.5 degrees from the center line. As mentioned in the introduction, rotation ratios seem to have a larger impact on penetration force than amplitude. At a lower rotation ratio, whatever changes in amplitude I put in there doesn't seem to have very much effect. But at the higher rotation ratio, both the amplitude 17.4, lower and a higher amplitude decrease the penetration force rather significantly. Moving forward, the research will look at amplitudes of 0, 5, 10, 15, 20, and 25 degrees, head oscillations of 0, 1, 2, and 3 per shaft extension. The hypothesis is that there exists an optimal combination of parameters which use the required penetration, force, and work. As predicted, the optimum lies somewhere around the 17 point, about amplitude 17 degrees with a ratio of oscillation near 2 rotations per shaft extension. For statistically robust data, each trial is going to be performed 5 times. Fast Fourier transform will be done, followed by low-pass filtering. Force is calculated from voltage measurements. Use the conversion factors described above for both the head and the shaft. Mean force and a maximum force will be determined from the smooth data. Work will be calculated as the area under the curve in the time force graph. Mean forces, maximum forces, and total work will be compared using ANOVA. The entire trial process involves filling the test arena and placing the robot, running the trial and collecting the data, emptying the arena and removing the robot, taking and weighing a sand sample, and resetting the robot for the next trial. The average time required to complete this entire process is about 25 minutes. You throw in the occasional maintenance of the testing machine, you get maybe an average of 5 to 10 minutes per trial. Should therefore take about 3 hours to run 5 replicates for each trial. And then there's going to be 16 different configurations to be tested. It should take 48 hours to complete the section of data collection all total. Um, Probably not going to be working continuously for 48 hours, so it's probably take about a week, 8 days to accomplish. 8 times 8 is doesn't make sense. Question mark in there. Suggested journal outlets include bioinspiration and biomimicry, experimental mechanics, integrative and comparative biology, Journal of Experimental Biology, Journal of Experimental Zoology, and Physical Biology. Project 2, looking at the effect of intermittency on forces required for burrowing. While burrowing, squamates exhibit either the simultaneous push-rotate movement of the head or the decoupled rotate-push-rotate movement. The reason that some organisms decouple the push and the oscillation is uncertain. Carl Gann suggested that this leads to a further reduction in required force. To investigate a hypothesis such as this and determine what ratio of forward penetration uh, to head oscillation is optimal, if such an optimum exists, the same robotic model will be used. It's hypothesized here the optimal parameter will be a shaft extension of 7.5 centimeters between each rotation, which corresponds to the length of the rotated head, and thus the length of the cavity that has presumably been excavated by the head sweep. In this case, two amplitudes will be programmed, informed by the results of Project 1, looking to see what amplitudes are advantageous. And code for the shaft and the head will be desynchronized in this case, so the head and the shaft movements will occur separately. For each amplitude and oscillation of the head will be performed, after which the shaft will extend. The extension distance following the head oscillation will be varied, and the forces involved will be compared. So extension distances will include 1.5 centimeters, 3.5 centimeters, 5.5 centimeters, 7.5 centimeters, 9.5 centimeters between rotations. Each trial again will be repeated 5 times. Fast Fourier transform and low pass filtering will be done. Forces will be calculated from the voltage measurements using conversion factor. The results will include mean and maximum forces, work calculated as the area under the curve in the time force graph, and mean forces, maximum forces, and total work will be compared using ANOVA. The time required for each trial should be similar to the time required for the trials in Project Uno, since the only difference in the procedure involves altering the code and controlling the robot, allowing for about 25 minutes per test, 5 replicate tests per trial, and 5 parameters. And the time for machine maintenance, this should take a minimum of about 10.5 hours to complete. Suggested journal outlets include bioinspiration and biomimicry, experimental mechanics, integrative and comparative biology, Journal of Experimental Biology, Journal of Experimental Zoology, and Physical Biology. And the third and final project involves head shape. It has been shown experimentally that different head shapes lead to different penetration forces, at least for artificial probes. Bio-inspired root-like shapes. Go ahead and deal with this. Larger diameters require more absolute force to penetrate. Let's take this section out. More gently tapered, pointier shapes experience lower penetration forces in general than blunter shapes. The slope of a head shape has been shown to be more influential on penetration force than pointiness, while diameter has a larger effect than either slope or pointiness. All of this is going to show that head shape influences forces required for penetration. So this suggests advantageous head morphologies for non-rotating intruder, but when the head is rotated, the situation here might change. A wider, less pointy shape could allow for more material to be moved out of the way during the head movement, therefore decreasing the overall forces required for movement, despite the fact that the shape is less pointy. It's also conceivable that head shape and kinematics are coupled so that it is difficult to refer only to the shape of an intruder's head when looking at these things. So, as mentioned before, among amphibians, different head shapes are associated with different movement strategies. Uh, More generalized bullet-shaped skulls associated with an apparently random and irregular pattern of head movement, either during the forward push or intermittently between them. The corkscrew type of motion, combining a rotational twist with a simultaneous forward penetration movement, is associated with the sharp edges on either side of the snout that shave material off the surrounding media. The laterally flattened keel snouted amphisbaenians exhibits a side-to-side rotation of the head, and the shovel snouted morphology with a dorsally flattened head rams its head with substrate and then lifts to pack material into the ceiling. However, the extent to which morphology in general is adaptive can be somewhat difficult to determine, and while there's much variation in head shape among animals that locomote through granular media, the extent to which head shape is correlated with burrowing forces is uncertain. The goal of this chapter would be to quantify the benefits in terms of penetration force and work for different head shapes and behaviors informed by the shapes of existing amphisbaenians. Head shapes will be printed using a Lawsbot 3D extrusion printer. Uh, it's held in place just by press fitting of the potentiometer and the screw that controls this, that attaches to the slider crank. So exchanging the heads is pretty simple. Um, I don't need this line. Three head shapes will be tested: the dorsally flattened shovel-headed shape, mediolaterally flattened keel-headed shape, and a more general rounded shape. Um, for this research, I'm not going to look at the corkscrew uh, shape. Kinematics to be tested will include vertical and horizontal head rotations at the optimal rotation amplitude and penetration distance between oscillations, indicated by the results of the experiments for Project 1 and 2. Trials will be repeated 5 times for each head shape and kinematic strategy. It is hypothesized there's an optimal strategy for each head shape corresponding to those strategies exhibited by living amphisbaenians, which head shapes are analogous. In other words, a keel-headed analog will experience lower penetration forces when employing the intermittent side-to-side head sweep, and the shovel analog will experience lower forces when employing the intermittent up and down vertical rotation. Again, the time to complete each replicate test should take about 25 minutes. Variables will include 5 replicates of 3 head morphologies and 2 kinematic strategies for a total of 30 trials. It should therefore take about 12.5 hours to complete the data collection for this project. Fast Fourier transform followed by low-pass filtering will smooth the data. Forces are calculated from voltage measurements using conversion factors described above for both the head and the shaft. Results will include both mean and maximum forces. Work will be calculated as the area under the curve of the time force graph. Mean forces, maximum force, and total work will be compared using ANOVA. Suggested journal outlets include Bioinspiration and Biomimicry, Evolution, Experimental Mechanics, Integrative and Comparative Biology, Journal of Experimental Biology, Journal of Experimental Zoology, Neuromorphology, and Physical Biology. Acknowledgements. All right, 132. Okay, not quite an hour. So that's not bad. That's not bad. This is probably good. Thank you for watching, my loyal listeners, viewers. Bye bye.